First of all, I thank Switch Ed for this wonderful platform. I am Edna Nima Verghese, a grade 5 student from Delhi Private School, keenly interested in the mysteries of space. I am a National Astronomy Champion of 2020.
My name is Himanshu Save. I'm a research scientist at the Center for Space Research at the University of Texas. I work with NASA on a few of NASA's projects. My keen interest is actually studying the Earth, where we live on this nice, beautiful blue marble, and try to understand the Earth and study the Earth from space. So that's my keen interest.
What was your key role in the Grace Followon, and how advanced is it from the Grace launch in 2002?
So as far as Grace Followon is concerned, I am the Science Operations Manager for Grace Followon. The measurements that we are making, the observations we are making on the spacecraft are actually not compromising the science. And so when the spacecraft is heating and cooling, we want to make sure that everything is working perfectly. The height of the altitude, these are two spacecrafts, they are separated by 200 kilometers, and so to make sure that the distance is fine, they are actually observing the things that we have to observe. So that's the primary goal, and so my role is to make sure that all of that is working properly. So I have to work with the operators of the spacecraft with our partners in Germany. And then the other part is actually doing a data analysis after collecting the data, and then producing the gravity maps, which then other scientists can look at and understand how, where is the sea level rising, where is the glacier melting, how much is the glacier melting, where are there floods and where are there droughts, and how much water has been lost, and stuff like that. So those sort of summarizes the things that I do.
Okay, sir. Next question. By observing changes in the Earth's gravity field, scientists can estimate changes in the amount of water stored in a region, which can cause changes in the gravity. So how is water and gravity interconnected?
Nice question. So let me start. So what is gravity, right? Let's start there. So any object that has matter, that has mass, has gravity. So if you have two objects next to each other, both of them have mass, and so this object will have a gravitational attraction to the other object, and this object will try to pull this object towards it. Same thing happens with the Earth and humans and the moon. One object is trying to attract the other one. So let me explain how the missions work. So these actually, here are little models of the satellites that are flying. And so this is how the actual satellite looks like, and this is 1:20 model. So the satellite's actually 20 times larger than this. And so there are different instruments on here. This is the GPS antenna on here. This is what we call the KBR. So this is where it's actually sending radio signals and then receiving radio signals when it's reflected back from the other spacecraft. And then these are the solar panels, which is giving it power. We have two of these identical spacecrafts. They're in orbit. They're about 500 kilometers above the Earth. And so what happens is, as they're flying over the Earth, say, for example, if they're flying above Himalayas, right? So now Himalaya is a huge mass sitting on the Earth. Now what happens is, when these are flying, the Himalayan mass is actually, because gravity, the first satellite is closer to Himalayas, and so it gets pulled towards it. And so as they are flying, the first satellite starts speeding up. And so the distance between the satellite increases, right? And so they fly over, and now the first satellite is over Himalayas and the second satellite is closer. And so this satellite slows down and this satellite speeds up. And so the distance between them decreases. And then they fly over it, and then this pulls back, and then so they constantly are doing this as it's flying over the spacecraft. And so we are measuring all of that. Now imagine next time you have rain. So say there's huge flood the next 2 days or something, and the satellites come back again. Now, when you add water, water has mass, and so the mass in the area is now more than it was last time the satellites came around. So satellites will come and do the same thing, but it will just do it just a little bit differently. The distance will be just a little bit different from the last time it did it. And that's the measurement we have from the satellites, and that's what we use to estimate how much gravity and mass there is. So to answer your question, then you get rains, you get droughts, you have glaciers that are melting, ice is melting, sea level is rising, and so the biggest change in the Earth system is actually the water. And the change in water means change in mass, change in gravity, and that's what we observe.
How do you decide the pathway of a satellite to orbit around a planet, as there are many objects orbiting with it? How do you sort of manage the space traffic?
Interesting question. So it has sort of a couple of components to it. So the first, the plan to where to orbit or how to orbit actually decided by what the satellite is going to do. If you have a satellite that is Earth observing, that you're observing the Earth over time, you want to make sure that you observe the entire Earth, right? So you are then in a polar orbit. And so you have to go over the poles and South Pole and North Pole and keep orbiting while this Earth is spinning around it, so you can cover the entire Earth. In some cases, you don't want to do that. You want to constantly observe one region. Say you want to take sort of image of India every time. And so you want to make sure that your satellite is actually always flying above India. As the Earth is rotating, the satellite is rotating above it and always taking the image of the Earth. And so stuff like that. So if you want to take the image of the Earth, you launch a spacecraft and it goes to a 36,000 kilometer orbit and then keeps observing the Earth, India. If you want to study Earth, then you launch it at the, say, 500 kilometers and then you observe the Earth. And so what you want to do with the satellite is what decides where you want to launch and how you want to launch it. Regarding the space debris there, that is getting to be a big problem now, but it is getting crowded. But even now, while it is still crowded, it's actually, I would say, it's the chance of collision is still fairly low, even at this point. But satellites are being launched pretty much every day now. SpaceX has launched already 1,700 spacecrafts for their Starlink project, which is basically the satellite internet, and they actually plan to launch 24,000 more over the coming years. And so that's going to be a lot of satellites up in space, and collisions is a big an important item in that sense. And so yes, we do have to be careful. We have to continue to watch whether we are going to collide with other spacecrafts and what's going to happen, get out of the way, and stuff like that. Yeah.
Okay, sir. Next, what happens to the satellites which are unable to be controlled from the ground?
So this is again, I think the same theme as the space debris, right? So you launch a spacecraft, and then either it fails or it's uncontrollable or it just finished its mission and is just sitting there. If there is a satellite that is anywhere around 500 kilometers, 600 kilometers or lower altitude from the Earth, it will eventually come down and burn up in the atmosphere. And depending on the spacecraft, the size, the shape, it might take about 25 years for it to actually deorbit and burn up. If you look at different spacecraft, so there's a satellite called Legios. It's a big chunk of metal. It's a perfect sphere, actually. It's a very nice sphere, and the whole plan was to have its nice and dense sphere. It's a 60 centimeter wide sphere, and it's 400 kilograms of weight, and it's at about, I think, 6,000 kilometers. That satellite, that after we launch, it will take about 10 million years for it to come down to the Earth. So it'll stay there pretty much like the satellite forever. Some of these satellites that are in the geosynchronous orbits up at 36,000 kilometers, they will take millions of years to actually come to the Earth. So once it's dead, or once it's not doing its mission, it basically becomes a space junk, and it keeps rotating around revolving around the Earth, and the next satellite that goes up, it becomes a danger to that next mission.
Okay, so recently it was a big news about the huge Chinese rocket debris to crash into the Earth. Similarly, many such parts are either burning on its own or falling into the oceans. What are the steps taken by NASA to stop such harm to the Earth in terms of sustainable development goals?
Again, the space debris part, right? It is several years ago, when we first started launching these satellites, this was not a concern. It was just a debris. You put it up there, it's big space, no one cares. But it's starting to become a big problem. NASA, so right now, for example, just several years ago, there's an understanding that anything you launch now, going forward, it has to be deorbited. So it has to be able to deorbit within 25 years after its launch. So you cannot just launch something and say, well, it'll come down and it comes down. So if it is not going to come down in 25 years, you need to have enough fuel on board to actually force it to bring it down after it's finished its mission, controlled re-entry. When it's actually burning through the atmosphere because of the friction, there are some guidelines as to what can be done. So you cannot have a huge chunk of metal falling on the Earth, on someone's house, and destroying it. So most of the spacecraft has to burn up. There are restrictions on how big of a metal can actually reach the Earth. Those studies are done before the spacecraft is launched to make sure that those things are adhered to. Before it starts burning up, you have to make sure that the fuel is all used up, that the spacecraft doesn't explode as it's coming down and creates more debris. Then you have to make sure that all the batteries are discharged, for example, because batteries can explode too as it gets hot, if they're really charged and stuff. And so those things have to be planned before they are launched now. Even for the spacecraft that are actually going all the way to geosynchronous, there are some guidelines about getting out of the way of the other satellites so that there are not, after you're done with your mission, so that space is given to the new missions that will come up. So you can't just sit there forever. You have to move out of the way. Since we have this theme of the space debris, I just wanted to share a little animation that was done by European Space Agency here. And let's see. Can you see this image here?
Yep.
And so what you see here is you have the Earth over there, and you see that big cloud of dust around it. Those are all the spacecrafts that's all debris that's floating around 500 kilometers over there. And then this big ring around it and so these are at, I think, 36,000 kilometers around. So that's sort of the traffic that's there in space that we have to deal with. Again, it's a vast space. It's not going to be it's not going to collide, but collisions have happened in the past, so that is a real concern. So that's what we're dealing with.
Wow.
They were really interesting questions, and so thanks for those questions. I had to scratch my head a little bit, but
yeah, I thought some of those questions were great. So I'm very proud of all three of you. Good job.